Welcome to Math with Professor V. In this video, we're going to go through several examples practicing taking derivatives of inverse trig functions. By the end, you're going to be a pro at this. If you want a little bit more context, you want to see the derivation of one of these formulas, then I'll link the video lecture here. But the purpose of this video is just to crank out a bunch of examples so that you guys can build up your skills. So the first thing you definitely need to do is memorize the differentiation rules for the inverse trig functions. And I'd say the most important, most popular ones are the first three here on the list: sine inverse of x, cosine inverse of x, and tan inverse of x. And the other three do come up, but not as often. And you can see also they're very similar. So derivative of sine inverse of x with respect to x is 1 over square root 1 minus x squared. The only difference when you take the derivative of cosine inverse is that there's a negative. Okay, that always made perfect sense to me just because we know the derivative of cosine x, not inverse, but just regular, has a negative. So I'm like, yeah, I just keep the negative. Okay. Then the derivative with respect to x of tan inverse of x is 1 over 1 plus x squared. Notice no radical in the denominator, and there's addition. And then the others here also, you can see some similarities. So cosecant inverse of x, secant inverse of x, they're identical. It's just that cosecant inverse has a minus sign. They both have in the denominator x times square root x squared minus 1. So notice the order of subtractions reversed here. It's x squared minus 1. And for sine inverse and cosine inverse, it's 1 minus x squared. And then cotangent inverse of x looks just like tan inverse. It's just that it also has a minus sign. So all of the inverse trig functions that start with the prefix co have a negative in their derivative. Look, and that's the same for regular trig. Cosine inverse, cosecant inverse, cotangent inverse. They all have negatives. And this is true for your regular trig derivatives. Okay? It just gets a little tricky when we have to do the chain rule, which is why I wanted to practice some examples with you guys now. So here we go. Find the derivative of the function, simplify where possible. We're going to start really nice and basic, and we'll build up the spice level. So the function is sine inverse of 5x. Now, I'm going to rewrite the derivative formula here. So the derivative with respect to x of sine inverse of x is 1 over the square root of 1 minus x squared. Now notice here, whatever the argument is for the inverse trig function, that whole thing gets squared. So look at the function that we're being given right now. The argument is 5x. Okay, so I'm going to have to square that whole thing. So f prime of x is going to equal 1 over square root 1 minus 5x squared. How are we doing? Yeah, you don't see sine inverse anymore. When you take the derivative, you have 1 over square root 1 minus whatever was in the parentheses squared. Now we do have to use the chain rule, right? Anytime the argument is not just plain old x, when you have a composition of functions, you have to do the chain rule, multiply by the derivative of what's inside. So not the derivative of 5x squared. That's where students get confused. You just multiply by the derivative of what's inside of 5x. Derivative of 5x is just 5. Okay, so when you're doing the chain rule, maybe you need to just look back here at the original. That's what you're taking the derivative of. Okay, and then let's just clean up and simplify a little bit. I'll just put the 5 in the numerator over square root. This will be 1 minus 25x squared when I multiply it out. And that's it, you leave it, okay? And if you're in the habit of rationalizing denominators, it's not a thing right now. It's not necessary for these problems. It won't make them look better. So get over that habit. I'm sorry. Okay, here, let's try another one. Y equals sine inverse of e to the 6t. So you could say y prime dy dt. It's not dy dx because you see how we have a function of t on the right-hand side. So y prime is going to be 1 over square root 1 minus whatever is in the parentheses squared. So that's going to be e to the 6t. Then I have to do the chain rule because whatever's inside the parentheses was not plain old t. I'm going to have to multiply by the derivative of e to the 6t. So the derivative of e to the something is e to the something. And then I have to do chain rule one more time because the exponent wasn't plain old t. So derivative of 6t is 6. Okay, take a second, marinate on it. I have 1 over 1 minus whatever was in the parentheses squared times derivative of just e to the 6t, not e to the 6t squared, no. Just the derivative of this e to the 6t times another 6. And then now we're ready to clean up. So I'm going to put 6e to the 6t in the numerator over square root. This is 1 minus. Do you remember your laws of exponent? When you raise a power to another power, you're going to multiply the exponent. So this would be e to the 12t. And then you box it. That's it. Okay, that's completely simplified. That's what we want. So we end here. Very nice. Okay, continuing on. G of x equals secant inverse of e to the x. Let me remind you what the formula is for the derivative of secant inverse of x. And I'm going to tell you right now, these inverse trig functions really are going to be important, especially when you get to calculus 2, okay? 1 over x times square root of x squared minus 1. In this case, I don't have secant inverse of x, I have secant inverse of e to the x. So that's going to go everywhere we have an x in the formula. So here we go. G prime of x is going to be 1 over, instead of x, I have e to the x times the square root of e to the x squared minus 1. So far, so good? Times, don't forget chain rule, derivative of what's inside, derivative of e to the x is e to the x. So take a second. How are we doing? Okay, good. Now look at this. One nice thing is that this e to the x in the numerator cancels with the e to the x that's in the denominator. And then I'm just left with 1 over square root e to the x squared, that simplifies to e to the 2x, very good, minus 1. And that's it. Okay? Good. Very good. Let's look at a few more examples. Now let's deal with some tan inverse. And I wanted to show you these two side by side so you can compare the difference, okay? It's very important that you pay attention to parentheses and where exponents are because it will significantly change the result. Okay, we have y equals tan inverse of x squared. If you need to remember what's the derivative of tan inverse of just x, it's 1 over 1 plus x squared. So since I have tan inverse of x squared, y prime is going to be 1 over 1 plus x squared squared times derivative of x squared, which is 2x. Okay, so when you have tan inverse of something, the derivative is 1 over 1 plus the something squared. In this case, my something was x squared, so I have 1 over 1 plus x squared squared. Then we do the chain rule, then I multiply by the derivative of just the something, just what was in the parentheses. Derivative of that is 2x. And then now simplifying, I can put 2x in the numerator over 1 plus, yes, that's going to be x to the 4th. Very nice. Now look at what's different here. Number 5, we have y equals tan inverse of x. All of that is being squared, okay? So we're going to do the chain rule again, but remember, you start on the outside, work your way in. So y prime, when you have the derivative of something squared, you take that exponent, you bring it down in the front, and you subtract 1. The new exponent is going to be 1 less. So I'm going to have 2. My new exponent is 1. And then don't change anything inside the parentheses. You leave it alone, tan inverse of x. Then now I'm going to do the chain rule and multiply by the derivative of what's inside. So the derivative of tan inverse of x is 1 over 1 plus x squared. Okay? So this time, you always start on the outside, work your way in, bring the 2 in the front, subtract 1, my new exponent's 1, leave what's inside alone. Then when you do the chain rule, you multiply by the derivative of what's inside, tan inverse of x. Okay, and then to clean this one up, there's really not much else to do. I'm just going to put 2 tan inverse of x in the numerator over 1 plus x squared in the denominator. Okay? Good, how are we doing? All right, we've done a bunch of chain rule. Let's practice with a different differentiation rule, the product rule. So y equals 2x to the 4th times sine inverse of x. Notice here I have a product of two functions, 2x to the 4th sine inverse of x. So we're going to use the product rule. So y prime equals, now there's a bunch of ways you might have learned the product rule. I just say each of the functions takes their turn having their derivative taken. So let's say 2x to the 4th. It's your turn. So the derivative of 2x to the 4th would be 8x cubed. But it's not sine inverse's turn. Nope, one at a time. So times, leave this one alone, sine inverse of x, plus, it's product rule. So every time you take turns taking the derivative, you're going to use a plus sign in between. Product rule plus. The letters go together. Okay, so you just keep adding everything together. So 2x to the 4th already had its turn. We're going to leave 2x to the 4th alone this time. Times derivative of sine inverse of x, which is 1 over square root 1 minus x squared. And that's it. Should we clean it up a bit more? I guess that last term I could put 2x to the 4th in the numerator. So 8x cubed sine inverse of x plus 2x to the 4th over square root 1 minus x squared. Okay, there we go. That was nice. That was nice. Let's do another one with tan inverse. Why don't you pause the video, try this one on your own. That will be a good testament to how well you're doing. You can watch me solve these all day and think, oh yeah, I'm following along. I know what I'm doing. But then the minute you have to do it by yourself, it's a whole different story. So practice by yourself more than less, you know? Okay, y prime, derivative of tan inverse of something is 1 over 1 plus the something squared. So in this case, I'm going to have the something squared. Yes? Yes, Professor V. Okay, good. Then you're going to do the chain rule. So you're going to multiply by the derivative of the something of rad 5x. If you don't know my shortcut for taking the square root of a composition of functions, let me show it to you now. You could rewrite everything to the 1/2 power, but that takes some time. So here's the shortcut. When you're taking derivative of a square root and there's something else other than x sitting underneath, you put 2 and the original square root expression in the denominator. And then in the numerator, you're basically doing the chain rule. You put the derivative of what's underneath the radical. So derivative of 5x is 5. Okay? So if you want a rule for it, if you have like y equals square root of f of x, y prime would be 2 original rad in the denominator, and then f prime of x in the top. That's the shortcut rule. Okay? Okay, we can clean up a bit more. So let's see. I'm going to put 5 in the numerator for everybody. I'll put 2 rad 5x in the front. And then this I'll put in parentheses 1 plus. Now, if I have square root of 5x, but it's squared, the radical is going to go bye-bye. So this is just 1 plus 5x. Okay? You can stop here. This problem's from the practice test in my Calc 1 class. Not pre-calc. Oh my God, if I gave this to pre-calc. The answer key has this. If you want to keep simplifying a little bit more, you could, because this rad 5x is rad 5 times rad x. And you could cancel this rad 5 down here with the 5 in the numerator. And if you canceled, you'd just be left with rad 5 in the top to rad x times 1 plus 5x. And perhaps that's more simplified, perhaps not. So I really leave it up to you, okay? If you stop right here, that's perfectly fine. You'd get full credit if you want to take it further. But don't worry about rationalizing, okay? If you want to, you can. But with so many of these derivatives, by definition, they have radicals in the bottom. So we just leave them there, okay? We can have another discussion one day why we even rationalized and why it's really not so necessary. But we need a whole video for that. I'll have to get honest and vulnerable. Anyways, okay. Here's one of my favorites of all time. It's actually from the textbook. It's not on my practice test, but I love it so much because it cleans up so beautifully at the end. Are you ready? We're going to have to do product rule, chain rule, the whole thing. So y prime equals, this is product rule because I have x times sine inverse of x. Do you see that? Okay, so they're going to take turns having their derivative taken. Derivative of x is 1. I'm going to leave sine inverse of x alone. It's not his turn. Plus product rule. So we're putting plus signs in between. Now I'm going to leave x alone times derivative of sine inverse of x, which is 1 over rad 1 minus x squared. Okay, so that first term's done. Plus, now I need derivative of square root of 1 minus x squared. So let's use our shortcut for the derivative of a square root. So you put 2 and the original in the denominator, and then you do the chain rule. So in the numerator, you're going to have the derivative of what's underneath the radical. Derivative of 1 minus x squared is negative 2x, right? Very good. So let's clean up now. Y prime equals, this is just going to be sine inverse of x plus x over rad 1 minus x squared. And then look, these 2's cancel. I have a minus sign, so I'm going to write minus x over rad 1 minus x squared. Very nice. Okay. And then, lo and behold, these are the exact same term. They're being subtracted, so they're gone. So our final answer, y prime, is just sine inverse of x. Oh, how lovely. Okay. I hope you were thrilled like I was right now. Couple more, just 2 more. H of x equals arcsin of x times natural log of x. So again, let's do product rule. Product rule. Okay, they're going to take turns having their derivatives taken. So h prime of x, it doesn't matter which one you do first, because when you do product rule, you're just performing operations that involve addition and multiplication. Both of those are commutative, so you know, as long as you only do one at a time, you're good. Derivative of arcsin. Arcsin is the same thing as sine inverse, just another way of writing it. 1 over rad 1 minus x squared times, leave ln of x alone, plus arcsin of x times, now we're going to do derivative of ln of x, which is 1 over x. Can we clean this up more? Just put everything as one fraction, so ln of x over rad 1 minus x squared plus arcsin of x over x. Don't leave it all floating. But that's it. Don't get a common denominator. Don't stress yourself out. Just stop here. Stop while you're ahead. Okay, last one from the practice test. Y equals negative cosine inverse of 6x plus 3 over 9. So remember, derivative of cosine inverse of x is just like sine inverse. It just has an extra negative on it. So y prime is going to be, did you notice though we already have an extra negative here? So I'll have negative 1 over square root 1 minus this stuff, that whole mess squared, yep, 6x plus 3 over 9 squared. And then I need, that's just so disgusting looking. Okay, then I need to multiply by the derivative of what's inside, 6x plus 3 over 9. No, you don't need to do the quotient rule. Please, don't stress yourself out unnecessarily. 6x plus 3 over 9, I can write as 6 over 9 plus 3 over 9, can't I? So then just take the derivative of it like that, term by term. Derivative of 6x over 9 is going to be 6 over 9. And then derivative of 3 over 9, that's a constant, so it'll be 0. Now, I'm not reducing this on purpose. Why? Because I can see into the future. Well, really, I've just done the problem enough times, but you'll be able to see into the future too with enough practice. So leave it. Don't make it 2/3, I promise. Here we go. Let's clean up. These negatives cancel. I'm going to put this 6 in the numerator, okay? And then we'll put the 9 out front. So this equals 6 over 9 radical 1 minus, and then this 6x plus 3 over 9 squared, I'm going to distribute the exponent, meaning I'm going to write it as 6x plus 3 squared over 9 squared, which is 81. Okay, we are not completely simplified because right now what I have is a complex fraction. I have a fraction inside a fraction. I'm going to take this 9 and distribute it underneath the radical. However, when I'm going to put 9 underneath the radical, if I take square root of 9, now that's 3. So if I want it to still be 9, I have to square it when I put it underneath the radical, since it's not under 1 currently, which means it's going to become 81, okay? So I'm going to rewrite this now as 6 over radical. My 9 is now an 81 when it's underneath the radical, and I still have 1 minus 6x plus 3 squared over 81. Do you see what just happened? Oh, good. Now when I distribute, things will just simplify beautifully. So I still have 6 over square root 81 minus, this 81 will cancel with the 81 here, and then I just have 6x plus 3 squared. Okay, the answer key just stops here. If you really want to get carried away, you could multiply this all out, combine like terms, factor out, a 36, yep, and then you can simplify a bit further. But if you stop here, I'll give you full credit. Do you want to see how it can keep going? Probably not. Okay, let's just stop while we're ahead. So that concludes the video. I know students were asking, we need more examples of these inverse trig function derivatives. It was a bit lacking, so hopefully this helps fill in some gaps. If you want to see even spicier ones, oh my goodness, I was going through the book, there's plenty, but this will be more than enough for the test that's coming up. And if you're new to my channel, please give the video a thumbs up, subscribe if you're not already. You can check out, I have full-length video lectures for all topics in Calc 1, 2, 3. If you need a review too, I have some trig, algebra, and pre-calc. And please follow me on Instagram, TikTok, Twitter, Math with Professor V. I'll be back sooner than later. Love you all. Bye.